The topic for today's lesson is data analysis, and in particular, things that we must consider in order to draw conclusions that are valid. When studying trends in data, it is important to consider the reasonableness of conclusions drawn. Sometimes there can appear to be a relationship between two variables, but in reality, there are other factors at play which affect the conclusions that can be drawn. In a cause and effect relationship, a change in one variable causes a change in the other variable. For example, buying more items at a fixed price results in a predictable increase in the amount you pay for those items. In our first example, we have a graph which shows the sales of high-definition televisions measured in $10,000s of dollars compared to the advertising budget for an electronics manufacturer. So on this scatter plot, we've got some data representing the advertising budgets in 12 markets across Canada. So each dot represents one of those 12 markets, or geographic areas, in other words. And on the x-axis, you've got the advertising budget, so the amount spent in $10,000s of dollars in that region, compared to the sales of high-definition televisions, also measured in $10,000s of dollars. Now, underneath the scatter plot, you've got the equation for the line of best fit and the correlation coefficient. And it says, describe the strength and the type of correlation. If the correlation coefficient is 0.94, that tells us there is a strong positive correlation. Part B says, do you think we can conclude that this is a cause and effect relationship? What other factors might influence this relationship? So if this were a cause and effect relationship, that would mean that spending more money on advertising would cause an increase in sales. That is probably not true, because at some point, the sales are going to max out. You can't just keep spending more and more money on advertising expecting to sell more and more televisions. So it's probably not the case that this is a cause and effect relationship. It's also possible that as technology advances, TVs are cheaper, and that would leave more profit, which then the company could spend on things like advertising. So in effect, you could have sort of a reverse cause and effect happening here, whereby in actual fact, the cheaper the TVs get, the more money you have left over to spend on advertising. So let's write that down. Probably not. As technology advances, it's also possible that TVs are cheaper to make, which would increase profit. More profit means more funds available for things like advertising. Then it says, is it safe to extrapolate to estimate the television sales if a market has an advertising budget of $350,000. Let's remember that extrapolating means that we would extend this line of best fit on this graph all the way out to where X is equal to 35, because if X is measured in 10,000s, then to get to $350,000, X would have to be 35. The question is saying, is it reasonable to do that? Extrapolation is not usually very accurate. Generally speaking, a line of best fit is only accurate for the data within which it is drawn. So we would have to say here, no. The line of best fit is only accurate for advertising budgets between 0 and $80,000. Okay, moving on. Outliers we have talked about previously. So an outlier is a point that does not follow the pattern of the other points in the data set. So we talked about how if we have a scatter plot, and within that scatter plot we have various data points. And for those data points, we could draw a line of best fit. And then out here somewhere, we have this other random point. This is what we refer to as an outlier. Now, there's one other type of point we have to be aware of, and that is another influential point, which is slightly different from an outlier. So if I have a scatter plot and I'm going to draw my line of best fit there, an influential point, it would be a point sort of not too far away from the others, but just far enough away that it would actually change the line of best fit some. Now again, my pictures aren't the best here on my iPad, but you kind of get the idea. So there is a subtle difference there. So an influential point is a point that lies a significant distance from the other points, but it greatly affects the slope and the y-intercept of the line of best fit. So we need to look out for both outliers and influential points when we are analyzing and drawing conclusions from scatter plots. Now, errors in analysis can occur for a variety of reasons, and some of them are listed here. It could be that you don't have enough data to analyze. It could be that linear regression, so finding a line of best fit, is being used for data that actually is not linear. It could be that the linear regression is applied when the correlation is actually quite weak, so we shouldn't be finding a line of best fit at all. It could be that the cause and effect relationship has been reversed. So we could be saying that X causes a change in Y, when in fact Y causes a change in X. We could be extrapolating outside of the reasonable range of data, so drawing a conclusion or making a prediction for a value that is too far out from the data set you already have. Not removing outliers and influential points prior to analysis, that we just talked about. And lastly, assuming cause and effect when it might actually just be a correlation or even an accidental relationship. In the example here, it says, describe the possible error in regression or analysis for each situation. So looking at the first graph, it appears as though when this line of best fit was drawn, this outlier was considered, because you can see that the line of best fit lies below most of the points in this data set. So before that line of best fit was drawn, the outlier should have been removed. So we're going to write the outlier should have been removed before regression, which is the process of finding the line of best fit, before regression was performed. Now in the second graph, part B, there we have a line of best fit drawn through only 5 points. And 5 points is not really enough to justify drawing a line of best fit at all. So for part B, we're going to say not enough data. For regression. And in the last one, we can clearly see that the trend in this data is not linear at all. It looks a lot more quadratic. So for this one, we're going to say the data is not linear. So linear regression should not be used. In other words, it doesn't make sense to draw a line of best fit for data that isn't linear to begin with. And that concludes this lesson.